In this video here, we're going to take a look at the vector product. So to begin with here then, just recall from Core Pure where we introduced the scalar product of two vectors. So the scalar or dot product, whichever you prefer to call it, of two vectors A and B is expressed as A dot B and is defined as follows. So A dot B is equal to the magnitude of the vector A times the magnitude of the vector B cos theta. And it should be obvious, but the scalar product produces a scalar. Now what we want to do here is define a new product that now produces a vector. So the vector or cross product, again, similar to the scalar or dot product, this is just another name for it. So the vector or cross product of two vectors A and B is expressed as A cross B and is defined as follows. So A cross B is equal to the magnitude of the vector A times the magnitude of the vector B sine theta n hat here, where n hat is just a normal unit vector. So theta here is the angle between the vectors A and B. So let's just visualize now the idea of the vector product and explore what happens as theta increases. So as we can see then, we have this diagram here, and this diagram then shows the vector product of two vectors A and B. So we've got the vector A, the vector B, we've got the angle in between those two vectors, theta, that's acting in this direction, as indicated by the arrow. And we've also got this vector here that's acting directly upwards. And this vector here, acting directly upwards, this is the vector product, or the cross product, of these two vectors, A and B. Now this diagram is also the same as the right-hand rule if you are familiar with this concept, but don't worry too much if you haven't come across the right-hand rule before. All it tells us is which direction or what direction the vector product of two vectors will act in. Okay? So to begin with here then, let's just consider what happens when theta equals 0. And what I would recommend here is that you just pause the video and have a think about this, right? So what would happen when theta equals 0? And also just think about what would happen as theta increases from 0 to 90 degrees. And again, as theta increases from 90 degrees to 180 degrees. So to get us started here then, if theta equals 0, then our two vectors A and B are parallel, and therefore the vector product is 0, as sine of 0 degrees equals 0. Now, as theta increases from 0 to 90 degrees, the magnitude of the vector product will also increase, and in fact, the magnitude of the vector product is actually maximized at 90 degrees. And then finally here, as theta increases from 90 degrees to 180 degrees, the magnitude of the vector product will decrease this time. So when theta equals 180 degrees, the vector product is 0 again, as sine of 180 degrees equals 0. Okay, so please do make a note of these last 3 points here. These are quite important to consider and be aware of. So if you haven't already, just make a note of these 3 points here. Okay, so that covers everything for this page here. Let's have a look now at how we actually find the vector product for two vectors. So let's have a look then at how we find the vector product here for two vectors. So if we're given these two vectors here, right, so we've got the vector A, which is equal to A1i plus A2j plus A3k. And we also have the vector B here, which is equal to B1i plus B2j plus B3k. Then the vector product of these two vectors here, A and B, is evaluated as follows. Now there's two ways to do this. I'm going to split this up into method 1 and method 2. So let's begin here then with method 1. So to find the vector product here of these two vectors A and B, so that's A crossed with B here, that is equal to the following here. So we have A2 times B3 minus A3 times B2, and that's for I here. We then have plus, we have A3 times B1 minus A1 times B3, and that's for J here. And then finally we have plus, we have A1 times B2 minus A2 times B1, and that's for K here. Okay. Now trying to memorize this result here, not the easiest, right? But the good news is this result here is given in the formula book. Off the top of my head, I think they do give it in column vector form or column vector notation. But obviously that doesn't matter too much, right? It's just the same result, just given in a different format. Okay, so that's method 1 here for finding the vector product of two vectors. So now for method 2 here, this is the method that I personally prefer, okay? And this is what we call the determinant method. So to find the vector product then of these two vectors A and B, so that's A crossed with B here, that is equal to the following here. So what we do then is we set this up as a 3 by 3 determinant here. So this is my 3 by 3 matrix here. We have ijk along the top row, a1, a2, a3 along the middle row. Obviously, that just comes from the vector a here. And then along the bottom row, we have b1, b2, b3. Again, that's obtained from these given vectors here. So that's for the vector b. So what we do now is we evaluate this 3 by 3 determinant here, right? So obviously, we just split this up into 2 by 2 determinants, right? Expanding along the top row here as well. So in that case, then we get I times by the remaining 2 by 2 determinants. So the way that we obtain these 2 by 2 determinants, just in case you forgot, right? We eliminate this row here, eliminate this column, and whatever's left over, that is our 2 by 2 determinant here. So we have A2, A3, B2, B3, exactly as required here. Going along this row then, we have minus j now. So this is always plus, minus, plus, so on and so on. So we get minus j. Again, we times this by the remaining 2 by 2 determinants. We cross this row here and this column now. So what we get left with then is A1, A3, B1, and B3, exactly as required. And then finally, we have plus k here, times by, so we have, well, cross this row out here and this column. As you can see, then we get A1, A2, B1, and B2, again, exactly as required here. Now, I personally prefer method 2 here. I do think this flows a little bit more naturally, right? And is a little bit more intuitive for finding the vector product. So rather than having to rely on the formula book, obviously there's nothing wrong with that, but rather than having to rely on it, I just personally prefer this method here. Okay. And I do make a note of that here. So either method is fine for evaluating the vector product, but it is recommended that you use method 2 instead of method 1. Okay. So there we have it. That's how we find the vector product here for 2 vectors. So before we have a look then at a couple of practice questions here, there is a few important vector products here to be aware of. So as we mentioned then on the previous page here, before we have a look at some practice questions here for vector products, there is a few useful vector products to be aware of, and you might find it useful to make a note of the following vector products. So starting off then, I cross with I, so these are just our unit vectors here. So I cross with I is equal to 0. And that's true also for j cross with j and k cross with k. So each one of these is equal to 0. And we also have the following useful vector products here. So I cross with j is equal to k, and j cross with I is equal to minus k. J cross with k is equal to I, and again, the opposite way here, so k cross with j is equal to minus I. And then finally here we have k cross with I, which is equal to j. And again, just in the opposite direction here, k cross with I is equal to minus j. Okay, so feel free to make a note of these. You might find these useful as you work through practice questions for vectors within Further Pure 1. Particularly if you sometimes have questions based on proofs and stuff like that. These properties can come in quite useful. Okay, so there we have it in terms of an introduction here to the vector product. I do appreciate that there is quite a bit to take in, right? So feel free to go back, rewind the video, and just make notes as you go. But that covers everything that we need here then for our introduction to the vector product. Let's just work through 2 practice questions now for the vector product. So let's just get started here then with question 1. So as we can see then for question 1, pretty straightforward. All we want to do here is find this vector product or cross product, whichever you prefer to call it. So we have I plus 2j plus 3k cross with I minus 4j here. So the way that I'm going to evaluate this vector product here is by using the determinant method. So what we have here then is I've got my 3 by 3 determinant here. Along the top row, we have I, j, and k here. We have I, j, and k, like so. Now along the middle row here, what I've got then are these coefficients here for this first vector. So I've got 1, 2, and 3. So 1, 2, and 3 here. And then for the bottom row, what I've got here then is the coefficients for the second vector. So I've got 1, minus 4, and 0 here. So don't forget the 0 right for k here. I've got 1, minus 4, and 0. Okay. So what we need to do now is evaluate this 3 by 3 determinant here. So what I'm going to do here then is expand along the top row here. It doesn't matter if you want to go along the middle row or the bottom row, but generally speaking, it's just easiest to go along the top row. So what I've got here then is I times by, and what I do now then, basically, you think about this here, is I cross this row out and this column here, and we then need to evaluate the remaining 2 by 2 determinants. If I cross this row out here and this column, I get left with 2, 3, minus 4, and 0. So we get 2, 3, minus 4, and 0. We'll come back to evaluating it in just a moment. Let's just keep going here along the top row. Now, for the next element here, so for the next 2 by 2 determinant, I should say really, this one now is negative. So we get minus j, like so. And then we get left with our 2 by 2 determinant. So I cross this row out and this column to get left with 1, 3, 1, and 0. So 1, 3, 1, and 0. Obviously, by this point, right, you should be pretty confident just, finding determinants like this. This is just core pure. But just in case, obviously, just recapping it here as we go. And then finally, we get plus k. So plus k. And then for our 2 by 2 determinant here, we cross this row out and this column to get left with 1, 2, 1, and minus 4 here. So 1, 2, 1, and minus 4 here. Okay. So let's just evaluate each 2 by 2 determinant here as we go. So we get I times by this 2 by 2 determinant here. So we do 2 times by 0, which is obviously just 0. We then do minus 4 times by 3. So what I'm going to get here then is minus 12, which is just positive 12 here. So we get 12i there. Okay, like so. For this 2 by 2 determinant here, then we do 1 times by 0, which is obviously just 0. We then do minus 3 times 1. So I get minus 3 here times by minus j. In that case, here we get plus 3j. Like so. And then finally here for the very last 2 by 2 determinant, we do 1 times minus 4. So that's minus 4. We then do minus 1 times by 2. So I get minus 6 there times by k. We get minus 6k there. Okay. And there we have it. So in that case then, the cross product here of these two vectors, I've got I plus 2j plus 3k cross with I minus 4j here, minus 4j there. That gives us, as we've already evaluated here, 12i plus 3j, and then finally minus 6k there. Okay, and there we have it. So nice and straightforward. That gives us the solution there to question 1. So moving on to the very last question here, then question 2, which asks us to find the sine of the angle between these two given vectors here. Now, to find the sine of the angle between these two given vectors here, we need to use the following result. So we're going to use them. Sine theta is equal to, so we have the magnitude then of the vector A crossed with the vector B, and that's all over then the magnitude of the vector A times by the magnitude of the vector B here. Okay, so to begin with then, what I'm going to do here is call this vector the vector A. I'm going to call this vector here the vector B, and this will just make life a little bit easier, right, as we work through this question. So to get us started then, let's start by evaluating this cross product here. So the vector A crossed with the vector B. So we do that underneath here then, the vector A crossed with the vector B. So again, just as we did for the previous question here, all I'm going to do then is use the determinant method. So we get our 3 by 3 determinant here. Along the top row, we have I, j, and k. So I, j, and k here, like so. Along the middle row here, then we have 3, minus 2, and 1. So 3, minus 2, and 1. And then finally, along the bottom row here, we have minus 1, 2, and 1. So minus 1, 2, and 1 here. Okay. So it's completely up to you which row you expand along here. I'm going to expand along the top row. Okay, so I get I times by the remaining 2 by 2 determinant here. So we cross this row and this column off, and we get left with minus 2, 1, 2, and 1. Okay, so minus 2, 1, 2, and 1. We then get minus j here, like so. Then we get our remaining 2 by 2 determinant. So across this row and this column, we get left with 3, 1, minus 1, and 1. So 3, 1, minus 1, and 1 here. And then finally we get plus k. And our remaining 2 by 2 determinant. So across this row and this column, and we get left with 3, minus 2, minus 1, and 2 here. So 3, minus 2, minus 1, and 2 there. Okay, like so. So let's just evaluate each 2 by 2 determinant here. So starting off then with this 2 by 2 determinant here, we have minus 2 times by 1, so that gives us minus 2. We then subtract 2 here. So in that case, we get minus 4 here. We have minus 4i there. To get us started. Now for the next 2 by 2 determinant here, we do 3 times by 1, which is 3, minus 1 times by 1. So in that case here, we have 3 minus minus 1, which gives us 4. 4 times it by minus j here. So we get minus 4j. Like so. And then finally here, for the very last 2 by 2 determinant, we have 3 times by 2, which is 6. Minus then, minus 1 times minus 2. So in other words, we have 6 minus 2, which gives us 4 there. So we get plus 4k. Okay, so plus 4k there. And there we have it. So this is the vector A crossed with the vector B. But we actually want the magnitude of this cross product here. In that case then, the magnitude here, the vector A crossed with the vector B, this will be the square root. So it's going to be minus 4 squared plus minus 4 squared plus 4 squared. So in other words, we just get 16 plus 16 plus 16, which gives us the square root of 48, which we can simplify to give us 4 root 3 here. Okay. So what we've evaluated here then is my numerator. Now let's evaluate the denominator here then. So we've got the magnitude of the vector A times by the magnitude of the vector B here. So for the magnitude then of the vector A here, again, this will be the square root here. So we have the square root. It's going to be 3 squared plus minus 2 squared plus 1 squared. So I get 9 plus 4 plus 1. And if we evaluate this here then, this gives us the square root of 14. Obviously we can't simplify that, so we'll just leave it as it is. Now for the magnitude of the vector B here, again, we get the square root here. We get the square root then of minus 1 squared plus 2 squared plus 1 squared. So altogether here then we get 1 plus 4 plus 1, which simplifies to give us the square root of 6. And again, we can't do anything with that, so we'll leave it in that form there. So for the denominator here then, we actually have the product of these two magnitudes here. So the magnitude of A times by the magnitude of B. So that's root 14 times by root 6 here. So if I just do that underneath then, root 14 times by root 6 here actually gives us the square root of 84, which we can simplify, right? The square root of 84 here, that is the same as root 4, root 21. So root 4, root 21, and obviously root 4 is just 2. So we get 2 root 21 there. Okay. So altogether then, what we've got here for sine theta is equal to, that's the magnitude of this cross product here. So the vector A crossed with the vector B, which we've evaluated as 4 root 3. So for the numerator here, we get 4 root 3. That's fine. Can't do anything further with that currently. So this is all over then the magnitude of the vector A times by the magnitude of the vector B here, which we've just evaluated, right? That is 2 root 21 here. So we get 2 root 21. Now clearly we can cancel down here. So what we get here then is 2 root 3 all over the square root of 21. And in its current form here, right, you could just leave your answer like this. This would be absolutely fine. But what I am going to do here is just quickly rationalize the denominator. So if we quickly rationalize here, right, times both the top and bottom of this fraction here by root 21. What I'd get here then is 2 root 63 and that's all over 21. So root 63, we can simplify that as well. Root 63, that is, that's root 9 root 7. So root 9 root 7, that gives us 3 root 7 here. There we go, I'm losing the ability to talk, but we'll get there. So 3 root 7 times by 2, so that gives me 6 root 7. That's 6 root 7 all over 21. And we can cancel down one more time here to give us 2 root 7. We get 2 root 7 over 7. Okay. And there we have it. So that is the sine of the angle then between these two given vectors here. Okay. So there we have it. That gives us the solution there to the very last question, question 2. And that brings us to the end then of this video here on the vector product.